Today let us talk about crash recovery systems. To understand the crash recovery systems better, first we need to understand how the data is being accessed and how the storage structures are there and what are the possible cases of failure. Once we understand these concepts, then we can talk about the implementation of better methods for recovery process. In this process, let us first talk about storage structures. What are the various possible storage structures that are available and which may cause problem for us and which are suitable for us to recover from the failure. Based on the nature of the storage and the speed at which they operate and the constraints that they have in the real time, the storage structures are classified into three types. One is volatile storage, non-volatile storage, and stable storage. When it comes to the volatile storage, which is actually RAM, temporary memory, like cache memory, right? And main memory also can be treated as a volatile storage because it is attached to the CPU. Or simply putting it, any memory that is attached to the CPU can be treated as a volatile storage because they are prone to crash or failure at any point of time. Simply we cannot depend on it 100%. Whereas when it comes to the non-volatile storage, like CD-ROMs, DVDs, external flash memories, right, tapes, all these things comes into non-volatile storage. But still, non-volatile storage is also prone to the failure. Why? Because a disk may be corrupted, even though it's an external thing that may be corrupted. A tape may be get destroyed or corrupted. External flash also may also get corrupted. So all these things are also prone to failure, but they are not that much volatile as a volatile storage. So secondary level. Whereas the third one, what is alternative for these things? So if everything fails, what is to be treated as a stable one? The third one is a stable storage, which is a hypothetical one. Basically, nothing is permanent, nothing is stable 100%, but a hypothetical way of treating the storage as a stable storage, where techniques like maintaining multiple copies of the same thing, same data rather, multiple copies, so that the probability of failure is very, very less. That is, comparatively with respect to other structures, the probability of failure is so negligible that virtually we can treat them as stable, 100% safe. If I have maintained multiple copies, even if one disk crash at a particular point of time, then I can recover from the other copies of the storage. And how it works is basically, suppose if I take 10 disks simultaneously, if I maintain 10 copies of the data, and if I assume that the disk may fail in 10,000 hours, then at any point of time one disk may fail, but the probability that all the 10 disks will fail at a particular point of time instantaneously is very, very less. That is how we treat them as stable storage. So theoretically we can assume that they are stable. That means they are not prone to any kind of failures. Even if one part fails, we can recover from the other. That's how we treat them as a failure. That too, these stable storages are maintained away from the database, physically away from the database, and they're stored in such a way that they're less prone to the fire or whatever extraneous influences. That is how we treat them as stable storage. Similarly, when it comes to the failures, there are three types of failures, again based on the way in which the failure occurs. One is transaction failure, another is system failure, and the third one is disk failure. The transaction failure, again there are two types of errors that may cause the transaction error. One is a logical error, another is a system error. In case of logical error, that the transaction can no longer continue because of the various reasons, like there is a bad input, or data is not found, or a overflow problem, resource limit exceeding, something like that. So even though the transaction is running, because of these logical errors, some kind of interruption may occur in the transaction processing. Because of that, it cannot execute further, and its impact may be there on all of the transactions which are linked to this. That is one kind of logical failure in case of transactions. And the system failure, where though the logical failure is not there, but there is a deadlock, something kind of a deadlock system. It's a system failure. It can be treated as a system failure. So the two transactions are tousled in a deadlock. That is an undesirable situation. And the transaction, however, can be re-executed in these two cases. The second way of failure is through a system crash, where there is a hardware failure or a mechanical failure that has resulted in the malfunctioning of the database itself. Not only that, there may be a bug in the database software or a bug in the operating system is also possible. So all such failures comes under system failure, because of the system, the database has stopped performing its regular actions. So this comes under system crash or system failures. And the third one is a disk failure, where the disks that are operating corresponding to the database may fail. The disks may get corrupted, or the reading head or writing head of the disk may get corrupted. So such things comes under disk failure. So these are the three types of failures that occurs on databases. Then what about the crash recovery mechanism? What is its functionalities, and how should they operate even while the database is running and when they crash? So it can be classified into two parts. One is when the database is running in its normal actions, in normal course of action, what the crash recovery mechanism has to do, so that when there is a crash, we can use this information, we can recover back. That is one aspect. The other aspect is when there is a crash, how the recovery mechanism has to initiate its action and a step-by-step process to be implemented, so that we can get back to the state of the Dbms where it was when at the time of crash. So the crash recovery mechanism again can be classified into two ways. One is when the database is normally running, and when there is a crash, how it recovers from the crash. Now let us spend some time on stable storage implementation. Let us try to understand this a little bit better. We have talked about this stable storage in the previous slide, and the stable storage implementation is done through multiple copies of the same database. Again, multiple copies, how to maintain these multiple copies is also an issue. And how do I recover from the crash if there is crash of one disk? Even though multiple copies are there, one disk may crash at any point of time, one copy may fail. So how do I recover back from the other copies is also an issue. And the time constraint and throughput comes into picture here, and we need to deal about the ways in which the multiple copies are maintained. We have RAID mechanisms. We talk about this RAID mechanism in physical storage systems lectures, but still here the point is that there are several ways in which we can maintain the copies. That's one issue. The other issue is that data is being transferred from the main memory to the stable storages in the form of blocks, where the size of the block can be varied from database to database and mechanism to mechanism. But we can define a chunk of the data as a block, and we can assume that no particular data is redundant on two blocks, and no data is spread across two blocks. So we can delimit every block. Now, even though the stable storage is treated as permanent, theoretically permanent, still there are problems implementation of the in the implementation of these stable storages in the form of transferring of the blocks from the main memory to the stable storage. While transferring these blocks from the main memory to the stable storage, still there are problems. Like if I want to transfer one block of data from the main memory to the permanent memory or a stable storage, there may be a possibility that the partial transfer of the block may happen, and at that point of time there is some problem in the main memory. So half of the block has been transferred, but half of the block is left in the main memory. That is partial failure or total failure. The block was not updated. A particular block was never updated, or the remaining blocks are updated, but this block was never updated. That's a problem. Because if you maintain multiple copies, even if you forgot to update one block, that is going to create a problem for us. So that is a total failure. This failure may occur while transferring the data content in the form of blocks from main memory to the stable storage. And how do I protect the media from the failure during these transfers is, first we transfer the blocks onto the physical storage or the stable storage block by block. Once we write one copy of the block, then we start duplicating it onto the another disk. Even if there is a problem in transferring the first block itself, again we can resume the transferring of the block. So if one block is completed, one block of writing is completed, then we can duplicate the block from there itself onto the second disk. So like this, multiple copies can be copied in a systematic manner, so that even if there is a crash during the transfer of these blocks, we should be able to recover back. Again, you may ask that while transferring the block, there is a failure and the system main memory has also failed at the point of time. Yes, there is a chance. If the main memory fails while transferring the contents onto the hard disk, so we should be able to recover back even that in the stage. We need to talk about those things one by one later. Now let us try to understand the data access in databases. There are typically two types of databases. One is in-memory database, another is database, part of the database is residing in the main memory and part of the database residing outside the main memory. That's a hard disk. If the size of the database is large and the main memory is sufficient to hold the entire database in the main memory, then we can process the transactions quickly and through the buffer and main memory itself. But in certain other cases where the size of the database is very huge and main memory is not sufficient to hold the entire database, then part of the database will be brought into the main memory from the external disk, and the remaining part will be maintained in the external disk. So in such cases, what happens is we have data transfers from main memory to the internal buffer, main memory to the external disk, disk to the main memory, and so on. So all such kind of data transfers also comes into picture here. Why we need to study these things? Because when there is a crash, when there is a recovery process, we need to understand the process of data transfer that is happening in such kind of databases. Now here, let us restrict our attention to only those types of databases where parts of the database is on the external hard disk, apart from the part of the database into the main memory. So here, what happens is whenever we require a data block from a disk to the main memory, we need to have the input-output operations. Again, let us once again understand that data is being transferred from main memory to the hard disk or hard disk to the main memory in the form of blocks. A chunk of data is divided as a block, and transfer of data will be occurring only in terms of blocks only. So either we treat a block is being transferred or not transferred, but partial transfer is not considered. That is how we treat the data transfer in between main memory and hard disk. The data blocks here are again categorized into two types. One is the buffer blocks and physical blocks. Physical blocks are the blocks of the memory or blocks of the data that is stored on the hard disk. And buffer blocks are the blocks of the data that reside on the main memory. So there is a distinction between blocks of data that resides in the main memory as buffer blocks and blocks that are residing in the hard disk as physical blocks. So now we need to access the physical blocks. The operations here, we are naming the operation as input B transfers the physical block to the main memory. A transfer of block from physical memory to the main memory, this external memory hard disk to the main memory, is treated as an input operation as B, input of block B. And output of block B is treated as the data block that is being transferred from main memory to the external disk. That is how we'll distinguish between the operations of blocks, input block and output of the block B. And here we assume that each data fits into only one block, and that is what we explained in the last slide also, that no data is spread across two blocks, and no two blocks will have the common data, and so on and so forth. So we need to have certain restrictions on that to understand the block transfers. So from here onwards, we talk about data transfers in terms of blocks only. Again, two types. One is physical blocks and buffer blocks. Now in this case, every transaction will have a private workspace area where the local copies of the data objects it accesses will be stored. And data transfer between the local copy of the data items for the transaction and the system buffer will now take place, and we are giving a different names for that as read and write of database objects. So here readx, that means the for the database object X, readx indicates assigning of the value to the database object X to the local variable that is stored in the main memory or the private workspace of the transaction Ti. So now we have one more level of transfer. It is readx, which is from the local copy of the transaction to the system buffer, and system buffer to the local copy. Similarly, writex assigns the value of the local variable small xi of data into the local copy of the transaction for the database object X. So that is how we give a naming for data transfers between local copy to the system buffer to the local copy. Whereas once the transaction writes, then that write is done in the local copy of the transaction, right? The immediate transfer of that data block need not be done to the external hard disk. Again, that can be done at later stage and at the point of transaction committing. So at the time of committing of the transaction, now the data transfer between main memory to the hard disk or the external disk and external disk to the main memory has to be ensured. Now whatever copies that are updated by the transaction in the local copy, they have to be ensured. The serializability, everything is, if it is ensured, then the blocks are transferred to the physical storage or the hard disk, and that operation of input output will take place at that point of time.